Hi guys, welcome to Learn Electronics Repair. This is the PCB off the MIG welder we were looking at on the previous video. The basic problem with this is kind of like threefold in a way. The LED comes on, the board powers up, but this is literally connected via a resistor to the 24 volt supply. The 24 volt supply comes in as AC and through this bridge rectifier, and this powers the board. Okay, you can see all this in part one. This is just a quick resume. Because I don't have the machine this comes off, I actually connected some wires here, and I'm putting my bench power supply on here with a 24 volt DC supply. What I basically found is this chip is a pulse width modulator. It has a 24 volt supply and it's basically oscillating at least on one pin. It is doing something, although I didn't investigate further. This resistor here visibly gets hot on the thermal camera. It's about 72 to 75 degrees. Now, to me, that is excessive. We can work out the wattage being dissipated, and it's quite a chunky resistor, but I honestly don't imagine that the circuit designer intended this to be that hot. What does this supply? Well, it supplies this chip. And we figured out that because we know this chip, which is a LM324, has a 3.04 volt supply. That seems very low to me. Now, the datasheet says that this can run from 3 volts to, I think it was 30 volts. So it can run in that range, but I'm very suspicious of the supply voltage on here. And the other reason, because this resistor also has 3.04 volts on here, and that connects directly to the power pin on here. So that is definitely powering this chip. The chip's drawing about 27 milliamps. Now, that seems a bit much for an op amp that isn't doing anything particularly. But I can think of a few reasons why the op amp would draw that sort of current, or maybe even more than that. So one possibility is that the chip is faulty. Okay? Another possibility is that it's oscillating. If it's oscillating, particularly at high frequency, it will draw some milliamps, okay? So it could be oscillating, possibly due to a fault condition, because I don't believe this should be drawing so much current. Third possibility is due to some input condition on one of the 4 op amps internally in here. It's driving the output to the rail or to ground, and it's driving something hard. So in other words, it's driving some load, and that's taking the current. But there's nothing particularly on here that looks like it needs any sort of load as such. Okay, so I'm a bit dubious that is the case. The other problem I found on here is that this MOSFET, the gate is floating. In part one, I was turning this MOSFET on and off by applying my multimeter in diode mode to the gate, and when I took the voltage off the gate, I could go to the drain and source and find it's 0 ohms, it's conducting, it's turned on. I could put my black meter lead onto the gate and I could switch it off and see it was switched off. In my opinion, I should not be able to do that with a working device. I should not be able to switch this on with my multimeter in diode mode. I may switch it on while the meter's applied if I use another meter to read across the drain and source, but it shouldn't float, it shouldn't switch on and stay on. Okay, that just seems really wrong to me. Now, I traced the gate of this, and it goes through, I think it was, it's one of these resistors. It goes through that one, and then it goes to a capacitor, so there's no DC voltage coming that way. And it also goes through this 100 kilo ohm resistor. And if you look at the 100 kilo ohm resistor, that then goes somewhere down in the direction of this op amp. And that's another reason why I suspect there's something wrong with this op amp, such as one of the outputs basically is floating, hence the gate of this is floating. I haven't traced it through, guys, enough. all this is kind of like a gut feeling. But a lot of evidence comes to this. I do have LM324. I have several of them, so we can change this. But I'd just like to make a couple checks and observations first. So the first one is with the thermal camera, this is hot. As I say, 75 degrees, something like that. Nothing else is getting hot. So you may be thinking, well, if this is drawing more power than it should, why does that get hot but this doesn't? Okay. Well, this comes down to Ohm's law. So let's just explain this. We'll do this on paper to make this very clear, and then hopefully you'll understand why, even if this is faulty and drawing too much current, it doesn't get hot enough so the thermal camera can see that. Okay, so what do we know that we have? We have the op amp. Power is on pin 4, ground is on 8, 9, 10, pin 11. Okay, so this is 0 volts, this is VCC, positive power. And this comes from a resistor which is 820 ohms, and the other end here has the 24 volt supply on. Okay, this here has 3 volts on. So we know the voltage across the resistor is 24 minus 3. There's 21 volts across here, and I actually measured that with my multimeter by measuring directly across resistor. I then worked out the current flowing through this resistor according to Ohm's law in the previous video. But I think this is important enough to just go through it again. Ohm's law, VIR. Okay, so the current, and what we do with this triangle, we just cover up the thing we want to know. So current is V over R. So it's 21 volts across the resistor divided by 820 ohms, okay? And this worked out, it was around 27 milliamps. Yeah, it's saying 25.6 milliamps, but bear in mind, these are not the exact voltages. When I actually add the exact voltages, and I'm not going to bother look up my previous video, it was about 27 milliamps. So we now know the current, and we can work out now the wattage being dissipated by this resistor. So watts equals voltage times current. The voltage across the resistor, we know it is 21. And the current flowing through it is 27 milliamps. This formula uses amps. So 27 milliamps is 0.027 amps. Okay. What's the wattage? Well, 21 times 0.027, 0.57 of a watt. This resistor is probably a 1 watt resistor, just judging by the physical size of it. And it's quite a small device, so that sort of wattage will cause it to glow on the thermal camera. And I say it was about 72 degrees centigrade, something like that. If that current is going into the op amp, and we don't know this for certain, but we're going to prove it in a minute, what's the wattage being dissipated by this? Well, first of all, we know the current flowing into it, assuming it is all flowing in here, yeah? Maybe the lion's share of it is, maybe all of it is, maybe none of it is, and say we will prove this. So the wattage here is the same formula, volts times current. What's the volts? Well, it's 3, because there's 3 volts coming in and 0 volts on the other terminal. So the voltage across it is 3 volts times the same current in a circuit. The current flowing in is the same as the current flowing out, assuming it all goes this way. I mean, there could be other things connected on here, we don't know. But anyway, not worried about too much. The maximum wattage, if it's all flowing this way, is 3 times 0.027, which is 3 times 0.027. It's not a lot, I'll tell you that now. 0.08 watts. Okay. 0.08 watts. And that is not enough to heat this chip up. Okay. And anything else that's being supplied by the 3-volt rail, if the current's going somewhere else, also isn't going to heat up with this sort of wattage. So that's why, although we can see this getting hot, and then from that we devised what the current is flowing, the wattage, and we can pretty much figure there's something wrong with the load connected to here. And other evidence suggests it's that. No matter where that current is flowing, with only 3 volts across it, the wattage and the load is going to be very low. Okay, hope you found that useful. This is, again, basic principles. You know, I don't like mathematics. I don't really use it on the channel much, but this stuff, really, you do need to know. Fortunately, it is very simple. But at least I hope you found that. So, how do we try to pin down even more so whether this is the problem? Well, the first thing we can do is measure the resistance to ground. So the 3 volts comes in on this pin, and this is ground. What's the resistance? Well, it reads a kilo ohm and climbing. So the resistance is not low at all. This kind of implies possibly the problem is that something's being driven by this hard, or hard enough to draw 27 milliamps. Let's go into diode mode. Because another possibility is something in here is breaking down with the 3 volts, and diode mode will stick about 3 volts into here. What we got? Oh! Well, that's quite low, yeah. I mean, look, that's like a diode junction. It climbed up to it. So that would sort of say that this point can't be more than 0.53 volts more than that point. And that voltage will probably increase with current. So by the time we get to 27 milliamps, yeah, this could be a 3 volt drop. That doesn't look right. I want to check something else on this op amp as well. I've just checked the data sheet. So there's 4 op amps in here, and effectively starting with non-inverting, it's in, out. Again, non-inverting, in, out. And then again with non-inverting, in, out, and in, out. Okay, so that's how they're all connected. Now this will have internal protection diodes, which effectively just stop the inputs going below the negative supply or above the positive supply. Pretty much that's what they do. So if we put the positive onto the ground supply, this is the reverse polarity to how the op amp would normally work. We should see here a diode junction. See, 0.713. You can't say what the value of it is, but what you can say that the inputs, the non-inverting on all the other ones should be the same. That reads short. Now there may be a good reason for that. And that one. This op amp looks like it's not being used. So a circuit designer would probably connect these 2 inputs to ground. So I'm not concerned about it. There's no tracks here. So this one we know is 0.713. This same input on this op amp, 0.697. That's close enough. Another one here, 0.725. That's close enough. And then if we look at the inverting inputs, well, that's quite low. It goes to a capacitor as well. That's quite low. What's on this one? Well, it actually goes to there, so much higher. And this one, much higher. So that is suspicious in itself. And then the outputs, 0.679, 682, very similar. 681, very similar. That one goes to here. 681, very similar. So the outputs sort of look okay. But this one, doesn't look good to me. I'll just measure across this capacitor because I'm interested now. If it had a shorted capacitor, it might cause some weird things to happen. Well, it's not short. Let's go to resistance. Yeah, 16 kilo ohms. So we have another reason to suspect this op amp. The real way to test this is going to be to cut the power pin. Okay, so if I cut the power pin, I should be able to do it low down. And if it still is this getting hot and there's still 3 volts on here, something else is causing the problem, I can just resolder that, yeah. So let's just chop this power pin. Okay. Do I have that disconnected? I'll just check. Well, I do now. Okay, so the power pin's disconnected on this chip. I'm going to power this up again and see what voltage I have here. Now, there is a possible problem with doing this. I don't know this board. But it could be so that this resistor is selected for this value so that when this chip is operating normally, we get a supply voltage on here, say 12. Yeah? And by disconnecting that chip, this could well go up to 24. And you'd think that may be able to damage something else. It's an outside chance. I don't see any other chips, and we know this has a 24 volt supply anyway. What's this capacitor? Well, that's 63 volt. This one here, 63 volt. This is a 63 volt. Looks like they all are. What's this one? Well, it's a 35. So again, that's above the 24. There's a little one here. I mean, this is a long way away from there, but we'll just check. 63 again, that one. So I don't think we're going to actually explode any capacitors. 63, 50, yeah, 50. I think there's one more which is there. Can't quite see that one, but hey, let's live dangerously. Let's have some fun. I'm also not going to apply this voltage for very long, okay? Just long enough to see what I have. Okay, so I'm ready to power this up. We'll just have a look at the end of this resistor here. This is the voltage. It was 3. What do we have now? I've disconnected the chip. Well, it's still 3. Okay, so that suggests either A, it's supposed to be 3, or B, it's powering something else, and that's what's drawing the current, okay? Because of the reading on here, and there's a fact that's a capacitor, I'm going to remove this. I'm going to replace it anyway. I don't see any reason not to do that, but I'm not totally convinced this is going to fix the problem with this, but let's see. So how to change this chip with basic equipment? Well, the safest way is also, if you like, the most brutal way. But what do we care about here? The chip which we're taking off the board or the PCB? Surely the answer has got to be the PCB in this case, because the chip is easily available. I have them. They're very inexpensive. This PCB is none of those things. Okay, so the way I'm going to do this is the same way I did that power pin. I'm literally going to cut all the legs off to take this off the board. I'll do it like I did that one so I can actually make those tests again when it's out of circuit. I'm interested to see. So the first thing I'm going to do is just get all the legs off the chip. And once I've done this, I'm just going to unsolder the pins, so you'll see how easy this becomes. Any other way you do this, especially considering what happened when the guy changed that, okay, maybe he's not so experienced at soldering, but there again, maybe you are not either. But if we do this, we have the best chance to not damage this board. So all these legs can go. I'm trying to leave a bit sticking out so I can get hold of it with the tweezers. You'll see in a moment how I'm going to do it. That one went all the way down. That was quite low down. Okay, other side. Right, so there's our now very defunct chip. But we can still test this out of circuit actually. So we'll do that in a moment, but let's continue with this job. So what we need to do now is just remove all these pins from the board, and then a little soldering tool or braid will be fine. You'll be able to clean all the holes out of the solder. Okay. And this way you're not going to damage the board. And you can do this with a lot of devices that have multiple pins like this. Particularly with these sort of PCBs and industrial electronics, this is the way to do it. Yeah, you really do not want to be damaging these PCBs. And some of them are not particularly well made. Strangely enough, some of them may be very old also. And a lot of old PCBs can't handle the sort of heat that modern ones can either. Okay. So, I won't bother use flux, I shouldn't really need it for this. Just a bit of fresh leaded solder. Go to the pin. Get hold of it if I can. Heat it up. And out it comes, yeah. First one. And it's just better basically doing the same with all of them. Yeah. Make sure you do get the pins out and they're not somewhere else on the board. If you've cut them very short, you're probably better do it from the other side actually. Yeah. Okay, so all the holes are clear. That is not the best job in the world, guys. This was quite a tricky one actually. Some of these PCBs are really a bit iffy to work on. But you can put it down to my bad technique if you like. I think I made life difficult for myself there by cutting the pins much too short. The reason I did that is because I wanted to test that IC out of circuit. Normally I would actually chop the pins off right at the top where they go into the plastic body. So, yeah, live and learn, Rich, yeah. Still, the good thing is the PCB is intact, yeah. And once I put the replacement part on, it'll actually look fine. So while the chip is off the board, a couple of things. One is I want to test that old one just with the multimeter again to see if it really is faulty, where I was reading that strange reading on one of these inputs. Although the fact I still have that 3 volts coming off that resistor, so that means the current must be the same because basically it is a potential divider between the resistor and the load. So it must still be getting hot. I didn't even need to check that. This may actually look alright out of circuit. Let's have a look. So as before, red lead to the negative voltage rail input. Okay, we're reading backwards polarity effectively. 739, 740, and that's the output, 682. Then this one's the other way up. 739, 740, close enough. 681. This is the one that read strange. Let's have a look. 730. Now reads okay, so it's something in the circuit that gives that reading. 680. 730. 736. 680. So that actually basically tests okay for that simple kind of cheap and nasty way to test these chips. While the chip's out, let's have another look at this PCB. So this is the one that had that very strange reading. Bear in mind this is reversed to normal polarity. Yeah, it's quite low. And this is a capacitor, I'm sure. Yeah, 100 nanofarads. And we don't see anything across the capacitor. Okay. So that reading is somewhere else. So it's this side. Maybe I didn't see it. So when I've taken the chip out, it's that pad. Just think of any internal layers. You know, this may have an internal layer, but you expect at least 2 internal layers. It's quite a thick PCB. Not totally sure about that. Okay, because I don't see how you could read that from that pin when it just goes to the capacitor here and it doesn't go anywhere else. And we don't read the reading from this side of the capacitor either, and we don't read anything across the capacitor. So it's not there. I don't get that. I really don't get that unless this board has some sort of internal layers, like a 4-layer board. Okay, but that seems a bit excessive for such a small PCB. Oh, can you see now, guys? So no, that's the track on the other side of the board, goes to the capacitor there. Oh, there's another track which goes down there somewhere. See it? Yeah, of course, it goes this way, so there's probably a diode or something there. Transistor. No, some more resistors and such like. Okay, well, mystery solved at least. While we're at this point, I'm also interested to know where else this goes. So we know full well it goes to the positive supply of this chip. Yeah. But where else does that go? So it goes under here. I don't think it comes down this way. They all join together? They might do. Does that go to here? I'm just trying to see where this track goes. No, it doesn't go to there. Hard to say without lifting that resistor. I may well have to do that. Goes off over this way, and there's another diode under there, which I don't think I checked originally. I think the only way to figure out where this is going to is to lift this resistor one end and lift this one end, and then let's have a look to see where that goes, because I'm still very suspicious. I mean, this thing is definitely getting too hot. Okay, so I've lifted that resistor, but I've also just noticed, so there's a diode here. Although it's marked D, this could be a Zener diode. Now, the 3 volts is on here, but if that's a Zener diode, then if we go from the other end, which is here, then that should go to ground, which effectively is here, and it doesn't. So that probably isn't a Zener diode, but it looks like it's kind of reverse bias. This does look like the cathode. I mean, that would make sense, that, you know, a resistor to a Zener diode, and maybe that's what's effectively holding the voltage at 3 even when I remove that chip, and maybe the Zener's faulty. There's another diode under here. I mean, that kind of looks like it should be a Zener, just the way it's wired, like the... I'm sure this is the cathode. Let's just go anode cathode. But that is a bit more like a normal diode. The Zener tends to be the slightly different forward drop than that, but it's just the way it's wired. But there again, this doesn't go to ground, so, you know, me sort of mulling it over, probably not. It does go down this way, but can't really see exactly where it goes unless I removed that. It goes up this way. Maybe I can just trace it without removing this one, but there again, I probably won't know if it goes to more than one place, so I'm going to have to lift that as well. So that's fairly easy to do. So it's next to this transistor. Okay. This has been soldered at obviously a previous repair, probably Roger who brought me this in. Yeah, I think I've got the resistor out. I've got it most way out, just go again. Okay. Where's that go? So we have a MOSFET here. This is the gate. Oh. I'm wondering, because I thought this gate was floating, which it seems to be, if this is being switched on and connecting something. Where's that go? That goes to there, which is this resistor, and the other end of the resistor goes to here, and this goes to something that's off the board on the connector, so that's not connected to anything at the moment, so it can't be kind of going that way. What we got now, we have another, now this looks like a Zenith BZX. Okay, so reads 0.26. Go the other way. Suspicious. Does the other end of that connect to ground? Certainly does. That's what you expect a Zenith to be doing. Let's get a good connection and keep a good connection. Okay, so it's possible this Zenith is a higher rated Zenith and it's faulty. I don't particularly suspect Zeniths of going low in voltage, but if that is a 3 volt Zenith, then we know this voltage rail is correct, and this thing is supposed to work at 72 degrees. Yeah, so let's get this Zenith out, or lift one end of it. In fact, I'd rather take it out. I want to see the markings on it. Right, let's try that without breaking it. Okay, I'm not going to mess about with this one like I did with that chip to some extent. I'm going to use the desoldering tool to just get us out. So one end, I definitely want this out in one piece, and they're kind of made of glass, so if you try to pull them out sometimes they just break. I really want to know what voltage this Zenith is. I think we can say with a great deal of certainty it is Zenithing at 3 volts. Okay. See if this will come without any hot air on it. Almost. This is not the nicest PCB to work on, I'll tell you guys now. Okay. That doesn't quite want to give it up. It has very stiff legs, so I can't kind of waggle it around with the vacuum tool, which is what I would normally try to do. Okay, we're going to have to heat this on the other side and see if I can just lift this one. If I get one end to come, that would be a good start. Let's get this out of the way. So, well, I've got the tweezers under it. Looks like that might be coming actually. Get a bit of heat from the other side. that one. Yeah. Yeah, it's out. Other end should be quite easy now in comparison to that one. Got a hold of the leg. I think it's actually moving around a little bit. Okay. It's out. What is this? Well, would you believe it? 85C12. That is a 12 volt Zenith. Yeah, that is a 12 volt Zenith. And it's connected directly from our resistor to ground. And unless there's something else holding the voltage down, this is the problem. I'm not going to try and power this up without this, because the 24 volts will probably go everywhere if I do that. But what I am going to do is replace this. In fact, I'll tell you what, let me test this actually. Let's have a look to see if it is faulty or not. Okay, this is actually my backlight tester, but I also use it for testing Zeniths. Okay, this is set to 1 milliamp. This will only give 21 volts out, so it's not going to hurt me. If I put it onto the 30 milliamps, 320 volts, it does hurt. I've done it before. What's it read? So it's a Zenith, so positive to the cathode, okay. .7. Oh, you little bitch. Yeah, right. Okay, so this is a replacement. This is a one end something or other. Okay. I believe this is a 12 volt Zenith. We'll certainly find out. Okay, so again, red to the cathode. That's a 12 volt Zenith. This is 1 watt. Now, I don't know what wattage the original one is, but I can say two things. I can say, A, it's about the same size. Yeah, very similar in size to that one. Okay. The other thing I can say is we know this is being fed via a 820 ohm resistor, and we know we have a 24 volt supply, and we know we should have 12 volts across this. Okay, so we can work out again the current flowing through our resistor, and then we can work out the wattage. So the wattage dissipated by the resistor and by the 12 volt Zenith should be the same, because the voltage across both is the same if this is fitted. Okay, let's have a quick look at that. So, bit of Ohm's law again. We know we should have 12 volts across the resistor, and we know the resistor is 820. So the current is V over R, which is 12, and this is going to be less than it was before, divided by 820. So the current should be 14 milliamps, yeah. So that's roughly half of what it was, just over. And the wattage is going to be that times the 12 volts, which is 0.175 watts, 175 milliwatts, okay. That's a lot lower than 560, was it, milliwatts? And the Zenith will be the same. So a 1 watt Zenith is absolutely fine. So I'll put the 1 watt Zenith in there, I'll reconnect the resistors, I'll replace this chip, and then let's try this. This bit of wire here is so stiff, I had to cut it to get it to clear away from here. I just could not bend that at all, and I can't get the leg of the resistor through. So you can see this track ends here, and we can see there's a track there which goes to the MOSFET. And I was thinking, what is this doing? And the only thing I can think of is that there's a track from here to the MOSFET on the other side of the board, and it's damaged. So this is another repair. I think if you look down here, we can actually see that is the case. So there is a track from here to here, and again, somebody has ripped the pad off there. Okay, so it's not only me struggling with this PCB a little bit. Yeah, that makes me feel just a touch better. So that goes in there. It now goes in easily. And I should, yeah, there's quite a bit sticking out now. So I should be able to bend this one over. If I can. Again, it's very hard. And solder it to here. Okay. So effectively remake this previous repair. Okay. It looks like, because this is down here, and this is where that faulty Xenon was, I wonder if somebody has tried to repair this previously. I'll ask Roger, or hopefully Roger, you'll reply in the comments here. Can you give us some history of this and how this happened? Did you remove this and just replace it, just wanting to test it, or do you think maybe somebody's worked on this before and maybe was onto the fault but didn't find it? They were kind of in the right area physically, at least. Yeah, that looks good now. I think that's the actual, no, that's the pin of the MOSFET. Okay, just clean it up and let's have a look. In fact, I actually add a little bit more solder to this side of it. In there, okay. I'll just have a look down here. I just want to see that that isn't shorted anything that way, because I've put this a bit further down physically than where it was. Okay. Let's just have a look what's down there. Yeah, I can see the Xenon diode and I can see the resistor, and it's not shorted against it, and the Xenon was the last component before the resistor. So that was okay, I think. Right. So this resistor back in, and then the chip. Now you may suggest to put this chip onto a socket, but A, considering the fault very much apparently was something else, and B, this is a welder. This is going to be used out. Yeah, it may be used in a mobile situation, it may be static or on like a trolley where it gets wheeled around if it's a heavy one. So this is probably going to be subject to quite a bit of vibration, and that really isn't the place where you want to start fitting ICs into sockets. Same with audio equipment that's used on mobile discos in particular, and carrozas, that's the Spanish word for like what we would call a float. That's a possession in English, carroza. Okay. And in those sort of situations, you don't want to put these things into sockets. So I'm going to solder this in. This board's a bit nasty, so I'm going to add some flux while I do it. Okay. Okay, so there's our chip. Hope you agree that's just fine, soldered in. Yeah, not too bad. I mean, these pads are a little bit bent, but it's looking good to me. Other side, yeah, all looks good. So let's power this up now and see what we have. But I'm confident enough to say we're going to have 12 volts on the end of here. Okay, bench power supply. 24, okay. This will probably read less current now. Let's have a quick look. So, attach the 12 volts. In fact, let's just zoom out in case anything really interesting happens. Okay, so we'll put the 12 volts on. Slightly less current, okay, 40 milliamps. But something didn't like that. See something go quick as I did that. Let's just have a quick look at this. Okay. The LED isn't on. Resistor. 12 volts. 24. So the interesting thing is now we have the 24, but the LED isn't on. Oh, it is on. It's just a bit dim. No, it's not. No, it's not on. Let's just have a look at this LED. So, That now has 21 volts on that end. Oh, the LED is on. Yeah, it is on. The LED is on. And brighter, actually, I think, than before. Okay, something goes click and this goes to brighter. Did you hear something happening on this board now? It's not a bad connection on the LED. Something's switching that. Right, so I think we can say that this is probably now fixed. I mean, I don't have any real way to test this, unfortunately, but this is very common with industrial electronics. When I actually did this as a full-time job in the early part of the 90s for a couple of years, I worked for a company, and their strategy was basically engineers would be given jobs to do. They would kind of like divvy them out a little bit, so some of us we consider to be better at certain things. I got all the microcontroller based stuff, basically microprocessor stuff, because that was my forte, or at least they thought it was. Yeah, some people got all the power supplies. I got all the various drivers and things off these kind of like computer controlled manufacturing machines. So that's what I did. Now the philosophy was there that if you found a definite fault like that, then you would send it back to the client, or rather give it to the field engineer who would take it out and fit it and see if it fixed it. With this one, the process of finding the fault was a little bit convoluted. Now, part of that is the fact the Zener diode was completely hidden. I did, during the discussion, say about taking this chip out and the voltage here may go up, and it should have occurred to me at the time that there would be a Zener diode. On here, they wouldn't rely on the load to effectively control the voltage here by the amount of current it's drawing. It made no sense. Should have realised that one, but hey, sometimes you just don't think about things at the time. So when I got to here, I thought, hang on, there's definitely going to be a Zener somewhere. They've hidden it. If I'd seen that, and it was marked with this BZY code, BZX, I knew it was a Zener straight away. I would have probably gone quicker at it. So I took a rather convoluted route, but I did test all the semiconductors that I could see. Yeah, and I'm fairly confident everything else on this board's okay. The one slightly strange thing is I can float the gate on here. Now, I was doing that when the board wasn't powered up. So it's possible that literally when maybe this chip is off, effectively the output is open, so that does float. I'm not going to go further down that rabbit hole because I found such a obvious and severe fault, basically no 12 volt supply, that it now kind of explains everything to me. Roger, you've been watching this one, my friend, my newfound friend. We've not met before, but strangers become friends, yeah, when they smile. So, Roger, I consider this to be fixed. If you'd like to come and collect it, I know you're going back to Ireland on Sunday, and let us know how you go on with it. Okay, so everybody, and Roger of course, hope you're happy with that. Hope you enjoyed watching the videos. I hope you've learned something, and I look forward to seeing you all again soon on Learn Electronics Repair. Ciao for now, guys.